Are some infinities bigger than the others? You know what? I am superior set than you. My set is unbounded from one side, and so I am infinite in size. Oh really? You think being infinite would make you superior? You probably don't know that I am a set of real numbers whose size is infinite too. And just for you to know, it is worthier than your set. This set comprises all the numbers that are algebraic, transcendental, rational and irrational that can be represented as a decimal, even if that decimal representation is infinite in length. Hence, 27 is a real number, as is pi or 3.14159. What do you mean? I thought I was infinitely numerous. You still are, but there is a difference between us. You are countably infinite, which means all the elements of your set can be well organized, whereas I am uncountably infinite, as the elements of my set cannot be sorted. Therefore, if you take infinite time, you could never know what comes after 1, 1.01 or 1.00001 or so on. There are more real numbers packed in between any two numbers than there are in the entire set of natural numbers. Let's have a look at it in detail. Infinity simply refers to something that is unlimited, endless, without bound. Until the end of 19th century, no mathematician had managed to describe the meaning of infinity beyond the idea that it is an absolutely unattainable value. George Cantor was the first to fully address such an abstract concept. He escalated the mathematical study of infinity by developing set theory, which led him to the surprising conclusion that there are infinities of different sizes. He even defined the notion of cardinality as the number of elements in a set and realized that infinite sets can have different cardinalities. The cardinality of natural numbers is known as alpha naught, and the cardinality of real numbers is known as continuum. In fact, Cantor showed there are more real numbers packed in between 0 and 1 as compared to the numbers in the entire range of naturals. He did this by contradicting logically. According to this, he assumes that the infinite sets are of the same size and then follows a series of logical steps to find a flaw that undermines that assumption. He reasons that the naturals and 0 to 1 subsets of the reals with equally many members implies that the two sets can be put into a one-to-one correspondence. This one-to-one correspondence is known as bijection. Bijective function can be defined as a function between the elements of two sets, where each element of one set is paired with exactly one element of the other set. Each element of the other set is paired with exactly one element of the first set. Note that two sets will have the same cardinality or will be of the same size if they are bijective functions. Think of it this way. One-to-one correspondences can be used to measure relative sizes even if the numerical counting is absent. Imagine two crates of unknown sizes, one of apples and one of oranges. Withdrawing one apple and one orange at a time thus partners the two sets into apple-orange pairs. If the contents of the two crates are emptied simultaneously, they are equally numerous. However, if one crate is exhausted before the other, the one with remaining fruit is more plentiful. It implies that if one-to-one correspondence fails, then one set is bigger than the other. Cantor thus assumes that the naturals and the reals from 0 to 1 have been put into similar correspondence. According to his assumption, every natural number n thus has a real partner Rn. The reals can be listed in order of their corresponding naturals R1, R2, R3 and so on. Continuing down the list, this mathematical method called diagonalization generates a real number p between 0 and 1 that by its construction differs from every real number on the list in at least one decimal place. Ergo, it cannot be on the list, which contradicts the initial assumption that every real number has a natural partner. In other words, p refers to a real number without a natural number partner, similar to an apple without an orange. Thus, the one-to-one correspondence between the reals and the naturals fails as there are simply too many reals. There are uncountably numerous, making real infinity somehow larger than natural infinity. Hence, it proves that there may be an infinite number of orders of infinities. And by now, most of your doubts would be clear. Did you understand the concept now? And also, how baseless our arguments are? Absolutely. Let's be friends. After all, we both are equally important. We hope you found the video interesting, helpful, and its content successfully swept all your doubts regarding real and natural numbers. Share this video with your friends and don't forget to like the video to keep us motivated. Let us know in the comment section how our video proved to help you clear your doubts and what new and interesting things you got to know from this video. We will see you in the next video with more knowledgeable content. Share the video and subscribe to our channel for more such information and lots of fun.